Jay Saldana, can you hear me now?
Okay, they can hear us now. We're good. So I'm going to go on mute, okay, John?
All right, thank you, Amanda.
Thanks. Hello?
Hello, Amanda.
Oh, hi. Just making sure you were still there.
I think we'll give it a couple more minutes before we start it.
Okay.
Well, good afternoon or good morning, depending on where you are, and welcome to the engineering team's webinar. The topic today is moisture and unvented attics, and we're going to have quite a lot of material. So ask that questions be held until the end. You can write them down within the webinar system. There's a pane there, questions, so you can write them down, and sure we'll have some time to go through that. And also, if we're lucky, we'll be able to go through maybe with the audio system. We'll see how that works out. So the purpose of today's presentation is really to give you some knowledge and fill you up in order to help you address problem statements like you see here. And that is that some homeowners and architects, and it could also be builders, general contractors, are concerned that using spray foam in an unvented attic will result or has resulted in moisture problems. And they're also concerned that mold could occur because spray foam is used. It doesn't help that people in the building industry are insinuating that moisture problems are widespread and systematic. And by systematic, mean that they are an inherent part of the system and basically could fail. So that's our goal. I think it's important to understand that unvented attics are fairly complex from a building science perspective. They're unique from other parts of the building, whether it's a house or a commercial building for that matter. They're subject to a lot of solar radiation at the roof, obviously, and during the night, there's a phenomenon called night sky radiation that some say is a factor too on what goes on in an unvented attic, clearly with regard to moisture and temperatures. So we see a lot of fluctuating temperatures and relative humidity values going on in unvented attics. And that's, largely because unvented attics are not directly conditioned space. And that's the assumption that we're making right now, at least for this presentation, that they're not directly conditioned. Thought I'd review some guiding principles of building science. This could be old knowledge for some of you, but the basic principle is that things in nature tend to equal out over time. And so heat flows from hot to cold, do that all the time, stack effect. Air pressure goes from air flows from high pressure to low pressure. Wind is a good example of that. And very importantly for today's discussion, Moisture flows from where there is high vapor pressure to low vapor pressure, or more commonly put, more to less. So moisture flows from where there is more of it to where there is less of it. Now there's a branch, I guess you could say, of on the building science side called condensation building science. So some points there are, the colder the surface, the more condensation could occur on it. So if a surface is 10 degrees Fahrenheit, for instance, it would see a lot more moisture or condensation occur on it than if that surface was 40 degrees Fahrenheit. There are materials also that are able to absorb moisture and therefore reduce the chances of condensation occurring directly on their surface. Wood materials are a great example of that. They can absorb moisture and so show up with condensation a lot less. Metal, such as sheet metal ductwork, does not have that ability to absorb moisture to any noticeable degree. And last point here is condensation usually occurs to air leakage rather than vapor diffusion. I think we've been hearing about that for decades, that most moisture is carried in air, and that is the big problem to solve with regard to condensation. So just looking at a U.S. climate zone map, in simple terms, the higher the climate zone number, the higher the condensation risk within the roof system, within the roof assembly, if you will. So much colder in Minneapolis than it is in Orlando, and therefore the higher the condensation risk. Now, that doesn't mean that condensation can't happen in climate zones 2 and 3. It certainly does, but within the roof system, it is a lot less likely, and that is why also why there are no vapor permeance requirements in climate zones 1 through 4, because the condensation risk is a lot less in those climate zones. So, all in all, the spray foam is a great system because it is an air barrier, or in code language is considered air impermeable, and most condensation is controlled. Most of the issues are controlled. And of course, in the colder climate zones, you're going to need a vapor retarder primer, or maybe the foam itself could be that vapor retardant. Now let's move to another area here. Let's understand a little bit more about relative humidity. This chart that you see here is from ASHRAE. And what it does, it defines, based on relative humidity, scale noted here on the bottom, what is considered the healthy zone, if you will, for building occupants. And ASHRAE defines it as being between 30 and 60% relative humidity is the optimum level in a building. So what that can mean in practical sense for you is if the homeowner is concerned that in their spray foam house they're getting humidity readings of 55%, relative humidity readings, then really they have no basis for concern. That is a very normal and good level. Of course, relative humidity levels can get too dry, which may cause some issues, or too moist, which may cause some issues, and we'll get into that a little bit more with respect to mold. But so that is something to keep in mind, that 30 to 60% relative humidity is optimum for minimizing health effects in buildings. So when it comes to mold and temperature and humidity, this chart here, you see, helps to explain a little bit about what the current thinking is of those kinds of conditions and trying to predict mold growth. So you see here we have relative humidity on this side of the graph, temperature on the top side Fahrenheit, bottom side Celsius. And there's a couple of research groups that have tried to outline, what are the conditions for mold growth. ASHRAE has said that between around 45 and 104 degrees and above 80% RH, there is a likelihood of mold growth and possible problems. The Europeans, at this point, have suggested that this curve outlines where mold growth could occur. So above it, mold growth could occur. So even at 85% relative humidity, but at temperatures within 40 Fahrenheit, might not be mold growth. But if you go to a warmer temperature at that 85% relative humidity, they're suggesting that there could be mold growth happening. I think a good takeaway here is this 80% mark. Now, if you read into the details of what these standards, this ASHRAE standard says about mold growth and this European research says about mold growth, is these relative humidity values for mold growth are based on a 30-day running average. So what that means is if an area like an attic sees 30 days of 80% relative humidity on average each day, then they would fall into this area, and there could be an issue. Now, if they're only seeing, say, 80% relative humidity for 2 weeks, 14 days, and then the other 16 days, they're seeing relative humidity on average at 70%, they would fall below the 80% line and would be, in that environment, would be considered too dry. So I think that's a takeaway you can use when talking to homeowners, architects, whomever, that criteria and the temperatures are pretty typical of attics. They're very much within 50 and 104. So the temperature values are nothing to be too concerned about. But it's really the relative humidity. We can say that below 80% on average for 30 days, if the humidity level is below that, then mold growth should be minimal, if at all. Now, the interesting thing about this, from this report by Building Science Corporation, is that they actually found areas where the relative humidity was higher than 80 when they examined some existing wall systems, and that there was no mold growth observed, even at higher relative humidity. So we may see this chart go up higher, these lines go up higher to higher relative humidities in the future. But right now, 80% is sort of the cutoff. And I do want to stress that is a 30-day running average. So just because somebody may see relative humidity of 90% for one day, if the next day it's 60, then that system, that area is considered dry enough that mold growth shouldn't happen. So I think a lot of it also has to do with expectations. And so I asked, is it reasonable to expect the same relativity conditions for an unoccupied, unvented attic as the main living area? I really don't think so. People do not live in this pictured area. It's concealed, it's not directly conditioned, so it's different than living space. So to expect 60% RH in this space, I think, is unrealistic. Now, are there systemic moisture problems? with unvented attic construction with spray foam? Well, when I've talked to people in the field, they tell me that they're not seeing mold and moisture problems. Now, occasionally there are one-off situations that do come up, and we'll get into that, what those causes may be. But in general, there doesn't seem to be any kind of systemic moisture problems that I can relate to. I think there needs to be a lot more proof to suggest that this kind of way of construction is a moisture problem, in spite of what some people in the building industry say. So let's look at some moisture sources from occupied activities. In the living area, you can have people and pets and plants, and so they all give off moisture. Their activities, and the more people, pets, and plants, quite honestly, the more moisture you're going to have. And that moisture is going to tend to go from a situation where there's more to less. So from the living space into the attic, if there happens to be less in the attic. So that's one moisture source area. Another, and this really, can be a situation for new construction or some, renovation work. Concrete gives off a lot of moisture. Now it takes 28 days for it to get to its stated structural strength, but it actually cures for longer than that. Sometimes up to 12 months. So during that time, slabs, basement areas are giving off moisture, and that could end up in the attic as well. Wood could be wet going into a building, and moisture from it could get into the attic. Wet wood could be in the attic. So those are a couple of moisture sources. Drywall compounds have water in them, and also paint and finishes can also give off moisture. And so new buildings usually take, the general rule of thumb, about a year to acclimate and have their moisture levels acclimate to their surrounding situation in terms of moisture levels. Now, I know we try our best to fully encapsulate attics and make them airtight, and it's very important that they be done so. But sometimes air leaks do happen into the attics. I mean, it's very hard to get 100%, but some of these leaks are not always obvious, and some of these air and moisture pathways can lead to problems. Here's a picture here on the left of an application. Here you see the foam coming against the drywall ceiling, and it's going around the framing. When they turned the lights off in this attic, they could see between the framing some daylight from outside. Now, it's not a big hole, obviously, but the idea is there that it's not a very obvious situation, hard to see any kind of issues here, but under the right conditions, if you will, wind blowing on that side of the building, moist air could end up in the attic. Here's another shot. Again, spray foam looks pretty good application here against the drywall ceiling and around the framing. Turn the lights off in the unvented attic, and you can see some points here that are allowing light, and some, need to be touched up. So being aware of these kinds of situations could help address homeowner concerns, if they're complaining about the attic being too humid. So have a thorough look and keep doing the thorough job that you're doing with regard to encapsulating attics. Never hurts to double check an application. Another moisture source is from bathroom exhaust fans and bathrooms in general. This is not an example of a bad situation, but if the bathroom fan is not venting directly to the outdoors and instead it's venting into the attic, well, it's going to deposit all that moisture from the bathroom below into the attic. And also air leakage around bathroom exhaust fans, around lighting outlets, could allow moist air from the bathroom to get into the attic. So those are some sources of moisture occurring from the bathrooms, and often people do see moisture issues in an unvented attic. It's not surprising to see them in the area above a bathroom. Now I'd like to switch to some design guidance. Now I know people don't design roof systems, but you may be able to pass on some of this info to builders, to architects, when you see them. Basically, the design concept is designing roofs for water vapor permeate. Mentioned earlier the need in cold climates for vapor retarder / barrier in unvented attic applications, whether that's a primer, an open cell, or the closed cell foam itself. But let's look at the water vapor values for certain water vapor permeance values for certain parts of a roof system. Remembering that the lower the value of permeance, the greater the risk that that material is going to trap moisture. So 6 mil poly might go on the inside of a cathedral ceiling. That has a very low perm value, 0.06, extremely low. And guess what's even lower? Something that is very common on roofs today, and that is self-adhered roofing membranes that go on top of the roof sheathing and underneath the shingles or the tile for water protection. Well, they are mostly extremely low water vapor permeance values at 0.03. Some of the most water vapor tight materials in the construction industry. I'm actually starting to see some such roofing membranes that have higher perm values that are not considered vapor retarders. So that may be something to watch out for. I think they're just hitting the market, probably more expensive, but the vast majority of the roofing membranes out there are very watertight at 0.03, and they have a high risk of trapping moisture wherever they're placed. Now, the old tried and true 30-pound roofing felt that's been used on a lot of roofing systems over the years has a perm value around 10. And when you look at spray foam, closed cell spray foam, it is basically around a 1 perm value. Now, it's going to obviously vary a little bit depending on the thickness of the foam. But to keep the conversation simple, if you will, usually if you say it's 1 perm, that works. And for open cell, a 10 perm value, again, it's going to change depending on thickness a little bit, but it's really about a 10 perm. So there's some common water vapor permeance values for materials in a roof. Now let's look at when these materials are used in a roof system design. And I know you're not designers, but this might help in your discussions with your builders and your architects and your homeowners too, for that matter, when they're making choices. So here's our roof system design. It's a cross section. Roof system. In this case, we're assuming a roofing felt, so that's 10 perms, and then OSB sheathing. And for this exercise, we're going to assume that the sheathing is wet. And then within the roof cavity, we have open cell spray foam, and so that's basically 10 perm as well. In a hot climate, you don't need a vapor retarder on that open cell. So in terms of drying of this wet OSB, going to have good drying potential to the exterior and to the interior. The perm ratings are very similar for the felt and the open cell. So it's a good system that can dry. And attic moisture levels shouldn't change too much. Now, if we take basically that same roofing system and we add a low permeance membrane to it. So again, this is something that has a vapor permeance that is very, very low, about 0.03. So what that does is that wet OSB sheathing is going to have an extremely hard time drying to the outdoors. And so drying is going to have to occur more to the indoors in order for this sheathing to dry out. And so could see increased moisture as a result in the attic because of this whole drying situation. Okay, let's move this roof system up to a cold climate zones 5 through 8. Let's have our 30-pound felt roof system, 10 perm, put on here. And in those cold climate zones, the open cell is going to need that 1 perm vapor retarder, or you use closed cell in here, which would be about 1 perm, let's say. So now the drying in this system will predominantly occur to the exterior. So there'll be reduced drying into the interior. So interior moisture levels within the attic shouldn't be affected. But we have good drying to the exterior in this kind of case. Again, if we change this roof system and we put that low vapor permeance membrane that we see on a lot of houses, drying of this wet OSB sheathing is going to be reduced extremely much to the exterior. The sheathing will want to dry or will dry more predominantly towards the interior, because you're talking about 1 perm on this side of it versus 0.03 perm on this side of it. So you could see more moisture within the interior of the attic as a result. So the takeaway is roof system choices matter a lot in terms of what happens in terms of moisture loading within an attic. And having higher vapor permeance systems in the roof would allow greater drying to the exterior. So reducing the amount of low permeance membranes is a good thing. Maybe they could just be used on the valleys of the roof, and 30-pound felt used elsewhere on the field of the roof, for example. Hopefully we'll see more higher permeance roofing membranes. The one I've seen is coming in at 16 perm. So that would be a good situation. Hopefully we'll see that kind of material more in the marketplace. So we looked at different mechanisms that can result in moisture getting into an attic. With regard to removing moisture in an attic, the HVAC system is critical to that. It is, even though the HVAC system is meant to serve just the living space, what it does in that living space affects the attic, because if all of a sudden the attic is has more moisture than the living space below, remember, moisture is going to go from a situation from more to less. So that moisture in the attic will try and make its way down into the living space. So the HVAC system needs to be correctly sized for the building, the house that it's in. And in retrofit situations, this might mean resizing it, which I know is expensive and can be painful for homeowners, but it's important because HVAC systems that are sized too large basically do a poor job at removing moisture. They do a poor job at dehumidifying the space they're in. That's because they don't run long enough, potentially, to remove moisture from the air. An HVAC system that runs only 5 or 10 minutes is not going to have enough time to remove moisture from the space. And we call that short cycling. So HVAC systems that are correctly sized would run on a more consistent basis. So they would run for 20 minutes or half an hour every hour, potentially. And that would give them a greater chance to remove moisture from the living space and consequently from the attic as well. Another approach related to the HVAC side is adding or utilizing better the humidity control aspect of the HVAC system. So, we know thermostats have temperature control. There's many out there that have humidity control. So the system would run when the temperature that is called for, the set point temperature is called for, is met. You could do the same concept with humidity control. So you could set a level of 55% relative humidity on the HVAC system, for example, and the system would run until that value is met. Now, it's not, there are some energy penalties, if you will, to that, but that's what can be done, and it is a good system in terms of also regulating comfort. Now, if you wanted to directly remove moisture from an attic, the ventilation systems are the way to go. Dedicated, adequately sized exhaust fans or energy recovery ventilators, ERVs, or heat recovery ventilators, HRVs, or air exchangers can be placed in an attic to get rid of the moisture in that attic. Exhaust fans, they just take the air out directly out of the attic in that case, just like they would out of a bathroom. So it's similar in that regard, just handling a moisture problem. The ERV and the HRV add some energy efficiency to that system. They would bring in outdoor air and have that conditioned to an extent. Now, for very humid locations, and you're thinking about the southeast, the Florida locations, having a standalone dehumidification system in an attic would definitely remove moisture in there. Or you could have a whole house system, dehumidification system, added to your HVAC system to give you that extra dehumidification ability. There are some penalties to having such systems, particularly in an attic. You have to deal with condensation removal. There would be a slight increase in attic temperature because these dehumidifiers generate some heat. To me, that's not a big issue. More the condensation removal would need to be dealt with. And they do use a bit of energy, but if people are really concerned about the moisture in the attic, dehumidification system, standalone system, can do it. They can also take in outdoor air so that it's a more efficient system, not drawing air from inside the house as much. So those exist. Now, eliminating the unintentional dumping of moisture in an attic, like you see here. It's not a spray foam attic, but point is, we've probably all seen this. Bathroom exhaust just being vented in the attic, and in a retrofit, we used to say that once that attic floor insulation is removed and the spray foam applied against the roof deck, that bathroom venting situation is not going to change. So it's just something that would need to be brought up to the homeowner in this case. That's a bad situation that doesn't work anymore. Not really sure it works as it sits anyway. Now I'd like to move on and discuss some of the latest unvented attic research. Got 3 studies that cover 3 different aspects, if you will. But basically, it's all unvented attic construction with spray foam. This first one is open cell spray foam research work done in the climate of Vancouver, British Columbia. So this is Climate Zone Marine 4. There were 2 long-term studies involved, 2 to 9 years in length. The real cool thing about this research was there was a research test hut, which was basically made up of a vented attic and 2 unvented attic situations. There was also an occupied house, and as part of this work, they also looked at 3 buildings and their unvented attic situations. Here is the research test hut. So it's sitting up on top of other buildings so that it's completely exposed to the weather. It was up for over a decade. The unvented attic system in it was, and the other systems were also heavily monitored for temperature and humidity conditions and moisture conditions. So some of the conclusions out of the study, particularly the unvented roof part, was that no visible mold could be seen in any of the open cell spray foam unvented test assemblies. So that was great. When they looked at roof sheathing moisture content readings, they were all well below 19%. Very significant, especially considering that this is a maritime, marine climate, I should say. So there's a lot of coastal air, moist coastal air, wind-driven rain, and the conclusion was that unvented attics prevent that. And the readings on the roof sheathing and the lack of seeing mold bear that out. We also did a comparison with regards to vented attics in that test hut, saying that it experienced high moisture levels during warm periods, when there's a greater potential for mold growth. If you think back to that chart we had, while in the unvented attics, higher moisture levels were seen in colder periods. Now, there weren't any moisture levels that were alarming. Just meant to say that since they were seen in colder periods, there was a lower potential of mold growth during those times. So the takeaway here is, even though there were some attic relative humidity levels that were sometimes high, no performance issues were discovered in the unvented attics. Now, the second unvented attic research I want to talk about today was sponsored by the Roofing Technical Advisory Committee of the Florida Building Commission. They didn't go into this being very spray foam friendly, surprisingly, really. Roofing contractors were complaining about damage and deterioration of roofs that had spray foam. So the Florida Building Commission decided to do the study. It consisted largely of a literature review. They did end up investigating a couple of spray foam roofs. They wanted to do more. It didn't work out that way. But they were looking for roof deterioration in those spray foam insulated roofs. They also did a study looking at the drying rate of insulated roof decks that are uniformly wetted. This was done in a laboratory setting. So some conclusions from that, and this wording here in this top bullet comes directly from the report, that the research team lacks sufficient evidence of widespread and systematic failures of spray foam insulated wood roof decks to conclude that premature deterioration of wood roof decks insulated with spray foam insulation is a problem in Florida. So they didn't find any problems based on what they were looking at. They did not recommend any changes to the building codes for unvented attics in Florida. When they surveyed the two spray foam unvented attics, they were both in Florida. One had open cell, one had closed cell. Both of those roof decks had moisture content levels of less than 6%, really dry. So that was very good. Attic temperatures, just so you know, were about 30 degrees Fahrenheit cooler than a vented attics situation that they were also monitoring it, which was good. Asphalt shingle temperature was 21 degrees warmer, a little bit higher, something to keep an eye on, if you will. The last thing that they did in this report was do some experimental testing of basically exposing different samples of a roof system, whether it was insulated with open cell or closed cell, with water, and seeing how well they dry. What they determined was that the closed cell foam insulation dried more slowly than samples having open cell foam or no insulation. Not exactly groundbreaking information there, but good to have it documented when needed. And it's important for the Florida market because it is vastly, predominantly uses open cell foam. They also found that there was little difference in the drying rate of the open cell foam insulation sample versus a sample with no insulation installed. So that was interesting to find out. And again, prove what we assumed, if you will, all these years, that open cell foam roof assemblies can derive well. Now, since those studies, there's been quite a bit of talk in building science conferences and on the internet about the Ping-Pong effect. Got a real cute name, and basically what they're suggesting there in terms of theory is that moisture goes in and out of the open cell foam and the roof sheathing, and it accumulates up to the peak of the attic. I wondered, is this an alarming situation? Are there durability problems associated with this? The proponents are saying that because the ductwork in the attic now is airtight, there's not a lot of duct leakage getting in there, and so moisture conditions are rising in spray foamed attics, particularly open cell spray foam. They thought this was a problem, and they were recommending fully conditioned attics, which obviously have a lot of implications for our industry. Did wonder if this really extends to go to this extent for all attics, that the unvented attics, they all be fully conditioned. Well, before we answer that and those other questions related to Ping-Pong effect, let's look at moisture and wall systems. And we've known stuff like this for decades. So here is a typical graph of moisture content levels. Moisture content levels here on this side. We have a time span. This is over 2 years. Looking at moisture content levels within different wall systems in different locations. And again, it's somewhat typical. You can have some very high levels and other very low levels. But the big takeaway is that these levels are very cyclic. Wintertime is the worst case for seeing moisture in wall systems within whatever the wall sheathing or the framing. And what happens is that they dry out as spring comes on, and then over the summer they get to their lowest point. And then as the new year comes on, they get to see more or experience more moisture, and that's really because they're experiencing less solar drying. And so this kind of situation goes on repeatedly in wall systems with wood materials. It's an accepted phenomenon by the building science community. And generally, if you ask them, they'll say it's not a big deal. The cyclic operation or cyclic situation of moisture in wall systems, as long as the drying occurs, as long as that occurs and these peaks are not too hot. So could this kind of knowledge apply to what's being said in the Ping-Pong effect too? Well, what it's led to is a research undertaken by the Spray Foam Coalition, which we are a part of, or sponsored by them, I should say, and undertaken by the Florida Solar Energy Center, looking at 6 homes in the Jacksonville, Florida area, so this is Climate Zone 2. All of these homes have been built after 2015 and have open cell spray foam unvented attics. We don't know at this point what product brands are in there. The roof sheathing in them have temperature and moisture content sensors, and the data collection for this has started in December 2017 and will be finished in March 2020 now. as it's been extended. So it's going to go through 3 winters. Now, at first, that first winter, here is the monitoring data, again, moisture content over time that we saw in these 6 houses. And at first, the values look very alarming. And we're going, uh-oh, what are we seeing here? We're seeing moisture content levels for several days being very high, between 20 and 30%, some even greater than 30 for several days before drying out. Well, those initial results were misleading because of the way that the monitoring effort was conducted. These houses were foamed up, and then to conduct the monitoring, the foam was cut out and very carefully, and then the monitoring equipment was placed on the sheathing, and then the foam plug, if you will, was put back in. And what was observed after a while was that those foam plugs were not adequately sealed. Now they have been with basically spray foam, so you have the same system. And what's being seen in this last winter, from December 2018 till May of this current year, is the moisture content levels now for the houses have dropped. Houses 3 and 6, by the way, are not going through this extended testing. So we feel that we've been vindicated, if you will, and that more importantly, the roof sheathing levels for moisture are within acceptable limits, according to this latest testing, and we'll see how things turn out in this upcoming winter as well. So, to conclude, what can we say about moisture in unvented attic? Well, using spray foam will prevent most condensation concerns by itself, since it is a good air barrier. Relative humidity below 60% is good for occupied spaces. That's well accepted. Less than 80% relative humidity on a 30-day continuous basis is not considered risky for mold growth in a space. So that's what we're seeing from US and European research. And field results indicate that even higher relative humidity levels may not cause problems. So 80% is a very conservative level to go by. There's many ways that moisture can enter into an unvented attic. Equally, there are many HVAC systems that provide moisture removal, and they can vary in cost and energy efficiency and difficulty. So it's something that we need to be decided by the builder, the homeowner, or whoever the architect. Oops. One more summary page here. Outdoor air leakage pathways. Spray foam unvented attics are not always obvious. We try to do a great job of encapsulating attics. Spend a little bit more time on those problem houses to see if outdoor air is coming in. Low permeance roofing materials could increase the amount of attic moisture in all climates. So staying away from them allows less problems to occur in terms of drying. Wet OSB can dry a lot better, and less moisture could be transferred into the attic. When you look at the latest field research, and we're talking about over several climate zones, unvented attic assemblies, which are, like I said earlier, not conditioned, they're performing extremely well. We're getting very good results. And so widespread conditioning of unvented attic, according to this research and other things that we're hearing in the field, does not appear warranted. Feel that the spray foam unvented attic system, if you will, is not broken, not a systemic problem. So with that, go to see if we have some questions. You have a few minutes. Let's see any questions there. I'm going to unmute people. See if I can take some questions that way.
Hi, John. Can you hear me?
I can hear you, yes.
My question is, it's a constructive question. This is Keeney in marketing. I just want to know if you shared how people can get a hold of either the slides or information from you after this is complete.
Yeah, I can definitely pass that on to you, and can take it from there.
Okay. And then there's going to be an email that goes out after this with a link to a recording of the webinar.
Very good.
Yeah, I have a question.
Okay.
On your slide where you were showing the open cell on the underside of it and the less permeable felt on the other side, showing that the moisture had less to escape one way. If we change that and we put the closed cell on the underside of that, what kind of problems are we causing at that point? Because that was the only way for the moisture to escape from the decking would be interior with the open cell. If it was the closed cell, does that restrict that breathability on that?
Well, if you're talking about a hot climate,
Well, it would really be either one of the climates. If you had that same situation where you had the moisture was getting in, and if you look at that chart you were showing, when you had the lesser permeability and the moisture could only get out from coming interior. So
right.
if that same slide had the closed cell on there with it being less permeability, now where's our moisture going at that point? Or does it get to the point to where that roof just fails because it can't get that moisture out either way?
Well, if you're talking about in a cold climate, remember that open cell is going to need a vapor retarder primer. So the interior spray foam part of that roof is basically going to be around 1 perm, because that's what that vapor retarder is going to add to that system. It's going to create that 1 perm coating. The closed cell is going to be roughly at 1 perm as well. It could be, half a perm based on its actual thickness, but the same we're in the same ballpark there.
Right.
The issue with the roofing system is a 0.03, which is an extremely low membrane system, or a roof felt system at 10 perm. So having a membrane system at 0.03 is going to really restrict the drying in both directions. And most of the drying is going to happen towards the interior, because 1 perm allows more drying than 0.03 perm. Here's a better look at it.
That's the one I was talking about right there.
Yeah, so 1 perm on the inside allows more drying than 0.03 on the exterior. So much better. Well, it is not a good situation. And so the drying of this OSB would happen a lot more slowly than if, for instance, if the open cell, for whatever reason, didn't have that vapor return.
Correct. That's what I was getting at. If we didn't have the vapor retarder on there that is required in our zone, then the drying would happen a lot quicker.
Right. Any other
Now,
questions? Go ahead.
I got a question. I typed it in, but must not be showing up.
Sure, go ahead.
Vaulted ceiling in a valley. So there's no way to vent the valley system. They're tearing the roof off from the outside. It's all finished tongue and groove on the inside. And I'm in climate zone 7, so all I spray is closed cell. Is leaving that gap between, the foam and that sheeting going to cause issues more potentially as far as, if the roof system gets wet and, for drying out, what's the best approach for that to almost guarantee that there's not going to be an issue down the road?
To me, the best approach is to make sure that there's going to be drying that could occur to the exterior. So not using a low perm roofing system, using a higher perm roofing system if that sheathing happens to get wet. I understand, what the concept is of having that air space underneath, but if that air, if any moisture gets into that airspace, if that air and moisture cannot escape, it's going to need a place to go. And with closed cell being about 1 perm, you want to have greater drying potential, if possible, to the exterior. So using roofing felt would be a good way to go.
Okay. What about synthetic underlayments? What are their permeability versus like a 15 or 30 pound roofing felt? How does that compare?
Yeah, those synthetic ones are what I'm calling low permeance membrane.
Okay.
The peel and stick kind of membrane. They have a very low water vapor permeance. They usually have that information directly noted on their technical data sheet, so you could see those values.
Sure. Okay. Another question. You back to near the beginning talking about the bathroom fan and having a lot of moisture in that area. So even if we do an unvented attic assembly, you're recommending we seal up fixtures and fans, at least in the bathroom area, just to prevent that excess moisture from getting into the attic. Back a little farther. You were talking about the bathroom. Yeah, right there. Oh, I lost audio. Can't hear you.
Sorry, if the drywall is very tight to the housing of this exhaust fan, then moisture would not get in between the drywall and the housing. And when the fan goes on, that moisture would be sent outdoors. Right. And that's what you want. So you want to control the system. So having, as much tightness, if you will, in these little areas would help control how the moisture in the bathroom is handled and that it is sent outdoors where it, won't cause any issues potentially within the attic.
Sure. Should that just be the complete house? Maybe just to control things better is to do air sealing on the lid as well as in conjunction with that unvented attic?
Well, we don't typically recommend that because we do want a little bit of air and temperature transfer between the top floor living space and the unvented attic. The unvented attic benefits by less humidity below it. Remember, moisture goes from more to less, so if it's let's say, a case where there's 70% RH in the unvented attic and 50% in the living space, that moisture is going to tend to try and get to that living space. So we don't necessarily want to stop that. It's going to be a slow event, but we don't want to make that ceiling airtight. Just really want to make sure that this bathroom fan, really does what it's supposed to, and that's handle spot ventilation in that area where there's, extreme amounts of moisture, where there's, more common moisture in other parts of the house. We don't need to make that airtight.
Okay.
We're a few minutes over our slotted time. Time for maybe one or two more questions. All right, hearing none, I'd like to thank everybody for attending, and we'll be sending that follow-up information your way. Thank you again, and have a good day.